Hello there, ROS developers, and welcome to a new open class. We are today in open class number 162, and we are going to be talking today a little bit about behavior trees. We are going to do an introduction to them and how to apply them to ROS2. So we have a super interesting class for today. So yeah, welcome everybody. I'm happy to be back after some weeks without classes. So yeah, as always, let me know please if image is good, if the audio is good, so that we can proceed with the class without any kind of issues. Then yeah, so let me just don't lose any more time. I'm going to switch right now to my computer screen so that I can also see the chat and everything. So let's go for it. There we go. Yep, let me come here to the open class area. Okay, hello Florencio. Also Ricardo says image and audio is good. Excellent, excellent. All right, then as always, I don't know if you are new to these classes, if you are already a veteran. In any case, the first thing that we always do is that we have to get a copy of the project. So today, for this open class, we are going to be working with a project, which is a ROS project that you can run online from any computer. So in order to get a copy of this project, all you have to do, super simple, is to click on this button that you have right above the chat, which says fork and open the class project. Yeah, so I'm going to click myself here right now, and this is going to do a couple of things. First one is going to create a copy of the project that I have created for this class. It's going to create a copy into your account. Yeah, so you are going to have this copy forever. Yeah, of course, for today, you are going to be using it today for following the class, but you are going to have it also if you want to access to this project next week or next month, you are going to have it. Yeah, so this copy of the project is going to be in your account forever. All right, so this is important in case that you want to come back to it later to review some things, whatever. All right, then as you can see, besides doing this copy of the project into your account, also it's going to bring you automatically to the project main page. Yeah, it might take some seconds here to fully load. As you can see, mine is currently being loaded. Today we have a project which is pretty heavy. So it might take some additional time to fully load. All right, let me see here some comments. 9 a.m. Pacific time seems like that is the answer. I don't understand your comment, Anton. Do these videos get saved? Yes, exactly, they get saved. Yeah, so right now we are live, but as soon as the class finishes, we are going to upload the recorded class into YouTube, into our YouTube channel. Yeah. So also you are going to be able to review this later if you want. Florencio says project takes a lot of time. What do you mean, to load, Florencio? Yeah. So as you can see, mine is still loading. As I was saying, so today's project is pretty heavy. Yeah, it weighs more than 1 gigabyte. We have some things there. We have some code related to behavior trees here inside the project, which is pretty heavy. So this is why it takes some more time than usual in order to fully load. Oh, I see, Anton. I see. Yeah, so the classes are always all the classes are always at the same time, which is 6 p.m. CET, Central European Time. They are always at the same time. Okay, so you can do the conversion based on CET time. 6 p.m. CET. Yeah, there you have it. Central European Time. All right, so meanwhile this is being loaded, let's not be here without doing anything. I want to get you introduced to the course, to the new course that we have published, which is the reason why today we are doing this class. Yeah. So today we are going to be talking about behavior trees for ROS2, as I just said in the introduction of the class. But behavior trees is a huge concept. Let's say there are many things, many different things that can be learned, that can be mastered. So today we are going to have a very brief taste. I try to reduce as much as possible while keeping it interesting. And but of course we are not going to be able to get deep into many things because of the time limitation. So these classes are 55 minutes long, and of course in order to really learn about behavior trees we will need many hours. But I have tried to keep it as simple as possible while trying to show many different ideas. Yeah. So basically, the idea for today's class is not going to be to obviously fully understand behavior trees and how to use them in ROS2, but to have a general idea. Yeah. I want to give this general idea so that you can grasp what is the concept behind using behavior trees for ROS2. Yeah, and if you are interested, then you can dive deeper into the concept. For instance, in this course. So this course we have published this week, and it's a complete course where you are going to be able to get much more detail and learn about many different aspects of behavior trees for ROS2. Okay? Let me go back to the project. Okay, this is still loading. It's taking a little bit longer than I expected, but it should be loaded pretty fast. Okay? So let me know, do you have any previous experience on behavior trees, on ROS2 maybe? We are going to be reviewing also a little bit of C++ code, all right? Or you have no idea at all about this behavior trees concept? Because behavior trees is, in the course, in this course and in today's class, we are going to be seeing some examples of how to apply behavior trees for ROS2. But let me tell you that behavior trees is, as a concept, as a framework, is independent from ROS2. So it can be used in many other platforms. For instance, in video games. Yeah. Of course, our academy is focused on robotics, so we are going to focus on this. Veronica says, behavior trees? No. I'm actually a new student researcher on ROS2. I have no experience on behavior trees. Okay, don't worry. So no experience is required for this class, okay? Anton says, started working on them with work, super interested in using them for applying our 3 robots to utilize them in an industrial setting. Electronic assembly, okay? So you are working with 3 different robots, Anton. Then you might be also interested in checking out about RMF, which is the multi-fleet management and so on, which could be interesting also for your case. Yeah, let me write it down here just in case that you want to check it out. RMF. All right, so my project has finally loaded. Here you have it. Then once the project loads, you are going to see that you have here automatically opened a Jupyter notebook. All right. Then here in the notebook is where I have placed the theory, images, the commands that we are going to be running. Okay. So basically, what I'm going to be doing is to follow everything that I have added here into the notebook. Okay. So you can come back here also and have a look at the notebook, in case that you get lost or that you want to review some of the things that we are talking about. All right. Then, first thing that we are going to be doing is to launch a gazebo simulation, okay? So how to do this? Well, very simple. In order to launch the ROS2 gazebo simulation, we need to execute these commands. So in order to execute commands, we need to have a terminal, a shell, right? Like you would do in a local computer, just the same. Then in order to open a shell, you have to click on this first button that you have on the bottom bar here, which says web shell. By clicking here, this is going to open a new terminal. Okay, now in this terminal you can type, this is a regular Linux terminal, so here you can type commands. For instance, what I suggest in order to be faster is to copy the commands directly here from the notebook. Yeah, so I'm going to select here the first command in the notebook, copy it with Ctrl+C, and then I'm going to paste it here into the shell. Yeah, and then again the same with the second command. There we go. So now, after some seconds, we are going to see the gazebo simulation loaded. Okay. There it goes. It's starting to launch the processes and everything. So for the first part of the class, we are going to be using only the behavior trees framework, okay, without the connection to ROS or to the simulation. And then at the end of the class, we are going to do an exercise where we have connected behavior trees with ROS2, where we are going to actually be using the simulation, okay? So we will actually use the simulation only at the end of the class, okay? In any case, we can launch it already now and leave it here running, okay? Okay, there it goes. Okay, here it has started gazebo. Okay, and if everything goes okay, we should see a simulation like this one. Okay, it's a Turtlebot 3 robot here in this kind of closed environment. Yeah, there we go. Yeah, so here I have my simulation loaded. Then I'm not going to actually be using the simulation until the end of the class. So for now, you can just minimize it if you want and leave this shell running here. Okay, don't close it, because if you close this shell, the simulation is going to be closed as well, all right? So now to keep working, you can just click here in the plus button in order to open another shell, yeah? And in this first one, we are going to leave the simulation running, all right? Okay, so now let's start giving a little bit of context. So behavior trees, as the name itself says, are basically, okay, trees that define behaviors, okay? And you can define any kind of behavior, yeah? In our case, of course, when we say behavior, we are talking of robot behaviors, yeah? So behavior trees basically allow us to architect a specific behavior for a robot, okay? So we can define behavior trees with the following characteristics. First of all, behavior trees are trees, yeah? So they start at a root node and are designed to be traversed in a specific order until a terminal state is reached, okay? We will see more about all this in a moment. Then these trees have leaf nodes that are executable behaviors. Yeah? And these internal nodes control the tree traversal. So how this behavior moves from one leaf, from one node to another. Okay? So another thing that I already said, but let me repeat it, is that behavior trees are independent from ROS2. Okay? So behavior trees are a framework and they can be used outside ROS2. For instance, in video games. Okay? So here we have, let me make this bigger. Here we have a graph that kind of illustrates this. Yeah? So here we have a typical C++ application that uses behavior trees without ROS2. Yeah? Then a typical C++ code that uses behavior trees is going to look like this. We are going to have some includes in order to include the behavior tree header files. Then we are going to have a series of classes that define the different behaviors. Yeah, we are going to have a section as well that it's written in XML code. Yeah, that architects the behavior. Okay. And then at the end we are going to have a main code where we register the different behaviors, the different nodes. We also start the tick, okay, which is a signal that it's sent at the beginning of the behavior. Okay, we will see a little bit more as we advance through the notebook. Yeah, and sorry. I have my thirst a little bit dry, so I need to drinking water. All right, and then here at the right side we have an application that is connected with ROS. Yeah. So you can have a look later. I don't want to get too much into detail because I prefer to show it. Yeah, rather than having a look here at a graph. I prefer that we move to the exercises and we are able to see the actual code because it's going to be easier to understand and to visualize. All right. Then, in this case, we are going to be working on a pretty high level of abstraction. Yeah. So when we are designing a robot, we have to take into account many different aspects, both from a high level of abstraction to a low level of abstraction. Yeah, so for instance, when we are designing the sensors, the actuators of the robot, so we have to go into a very low level of abstraction. Yeah, but now for designing these behavior trees, we are going to move to a high level of abstraction. Okay. For instance. This is a typical design of a behavior tree for a robot, okay? As you can see, here we have three main tasks, which are find ball, pick ball, and place ball, okay? Sorry. All right. Yeah. So here, we are we are designing a behavior for a robot to find a ball, pick this ball, and place it in another area, for instance. Yeah. So how would we define this behavior as a behavior tree? It would be something like this. Okay. Yeah. So find ball here. We are defining find ball as a simple block. Yeah, of course, in order to find a ball, there are many things that we should take into account. Yeah, like in order to find the ball, we will need to use some sensors that detect the ball, etc. Okay, but for designing a behavior tree, we are not going to pay attention into all those details. Okay, we are going to stay at a higher level of abstraction. Yeah? Does it make sense? Then here we can see blocks like this. And we can see some symbols here like these arrows, these question marks, right? So these are special blocks. Yeah? These ones are known as sequence nodes. Okay? And the ones with a question mark are known as fallback. Okay? What do they mean? They mean that the sequence nodes, these ones, in order to succeed, they need to receive a succeed signal from all their childs. For instance, this node has 3 child nodes. One is find ball, the other one is pick ball, and the other one is place ball. Yeah? So in order for this one to succeed, all 3 of its childs have to succeed. Okay? This is known as a sequence node, and it works as a logical AND door. Okay? In other terms. Now, what about the fallback, which are these ones? The fallback are going to return succeed as soon as one of its childs returns a succeed signal. Okay? So for instance, it can happen that the first one returns a failure signal, but the second one returns a succeed signal. Yeah? Then this is going to give a succeed signal in the parent. Okay? Okay. We are going to see this better in a moment as well, okay? But at least this way you can have a general idea of what is going on here, okay? Yeah? Any questions so far? Can we continue? Shall we continue? So far so good, says Garrett. Perfect. Okay. Then, yeah, so let's just start doing some quick examples. So we are going to start by running and having a look at a basic behavior, at this behavior, in fact, without the connections to ROS2, okay? So we are going to be running now and visualizing a C++ application which connects only with the behavior tree framework, okay? So right now we are not going to do any connection to ROS2, okay? We are going to be testing the behavior tree framework by itself, all right? Then let's move to this exercise here. So here we are going to be running a behavior, which is this one here. But before running it, let's have a look at the code, okay? So now, in order to have a look at the code, we are going to open the code editor, yeah? It's this second button that you have here in the bottom bar, which says code editor. If you click here, this is going to open the code editor, which is going to give you access through a graphical interface to all the files and folders that are inside this project, yeah? So in this case, we can go to the ROS2 workspace, SRC folder. You have the path also here, okay? BT course files here, first folder, BT course files, and here we are going to open the behavior tree.cpp, yeah? And finally, inside here, we are going to open the course_BT folder. Yeah, and here we are going to find a series of CPP files. Yeah? In this case, the one that we are going to open and have a look at is this first one, BT U2 exercise 1 CPP. Okay? So, this is C++ implementation code of this behavior tree. Okay? Then so this would be the design of the behavior tree, let's say, yeah? The logical connections of the behavior tree. And here we can have a look at the implementation, the actual implementation in code of this. Yeah. Then also keep in mind the structure that we saw quickly here in the first graph. Yeah, where we have the includes, we have the definition of the classes, we have the definition of the logic, the logical connections using XML format, and finally we have the main. Okay. Then let's come here to our code, and we can see that we have here the include of the behavior tree header. Yeah, and here we start seeing all the class definitions. Yeah, so we have one class here which is called approach ball. We have a second class here which is called find ball. Another class here which is place ball. Yeah. So if you come here back to the notebook, you are going to see, hey, this is find ball. Here we have place ball, approach ball, grass ball. Yeah. So all these nodes that you can see here, all these nodes, these leaf nodes, are defined into my application as classes. Okay. And these classes are going to return either success or failure. Yeah. Okay. In this case, for instance, for the approachable class, I'm going to return success. Always. Okay. So this is a simplification. So for some of them, we are just returning success directly. Okay. As you can see, we have here the gripper interface. The ball closed, ball grasped. Yeah, these are some helper classes as well. Okay. Now, down here, we have the definition of the behavior tree that reflects the logical connection between all the different nodes or robot actions. Okay? And as you can see, this is implemented in XML code. Okay? So we have the root, we have the behavior tree tag here, and inside the behavior tree tag, we have this sequence. Okay? You can see that we have a sequence defined. This sequence is this one here. Okay? Remember that these ones are sequence nodes, and these ones with the question marks are fallback nodes. Okay? So in this case, we have a sequence which contains find ball, pick ball, and place ball, right? So we have a sequence which contains the find ball, the place ball, and in between it has another sequence, which is this pick ball sequence, right? Yeah? And inside this sequence, we have two fallbacks, right? Inside this sequence, we have one fallback and another fallback. Yeah? And each of these the first fallback has the ball close and approach ball. Yeah? Ball close and approach ball. And the second one has ball grasp and grasp ball. Okay? Do you see the relation between this XML code and the design of the behavior tree here? Yeah? Can you see the relations? Yes, okay. And each one of these has its definition in the classes, okay? Yes, it's pretty interesting. Kind of like nested loops. Yeah, kind of, Garrett. Yeah. Okay, then finally we have here the main function where we are registering all the nodes. Yeah. we are registering some simple conditions. Also, we start the tick from here, yeah? This tick basically is that whenever we start the behavior, a tick is going to be sent from the root of the behavior, which is here, yeah? It's going to be sent down to find ball, yeah, this tick. Then if find ball succeeds, a tick is going to be sent to the next one, which is pick ball, yeah? And then we are going to enter here, and if pick ball succeeds, this tick is going to be sent finally to place ball, and so on, okay? All right, so let's execute it. Let's go and execute it now. So in order to execute it, you have to execute these commands. So let's come here to a new shell, okay? Remember, don't close the first one where we have the simulation running. Let's open a new one here. And here, let's start copying and pasting the commands. There we go. We do a source, we come here to the folder, to the CourseBT folder, and then here we are going to execute this behavior. Okay, BT U2 X1. Okay, and here we can see the output of the behavior. Yeah. So, which is this one as well. Then, here we have a short analysis of the output that we have received. Yeah, so let's see if we can go step by step and understand what's going on here. So, the robot task can be comprehended as one sequential task. The analogous is an AND logical function. Yeah, so this is a sequential task. Yeah, so it can be analyzed as a AND function, okay? So we need this first one to succeed in order to move to the next one, yeah? And in order to have the whole behavior succeed, we need that all the childs succeed as well, okay? Then the robot looks for the ball. The robot finds the ball, so the node prints ball okay, yeah? So the first behavior that is executed, we can have a look at also here, yeah? The first one is this find ball, okay? Then this find ball, if we have a look at the code, at the class find ball, yeah, this is going to return success, right? Perfect. Then we are going to move, as this first one is going to return success, we are going to move to the next one, yeah? And the next one is this sequence, yeah? Come here, this one succeeds, so we move to the next block, which is this big pick ball, which is also another sequence, yeah? Then we are going to start with the fallback here in the left, yeah? So we are going to analyze, is the ball close to the robot? Yes or no? Yeah? So ball close in this case, ball close is going to return failure. Yeah? Ball close is going to return failure. So this first one is going to return failure. Then I'm going to move to the next one. Okay? Why? Because this is a fallback node. Yeah? It's not a sequential node, it's a fallback node. So even if the first one fails, I'm going to analyze the next one. Yeah? Then the second one, which is approach ball, is going to return, we have it up here, approach ball is going to return success, yeah? So this first one is going to return failure, the second one is going to return success, yeah? But as we said at the beginning, fallbacks are going to be success as soon as one of its childs returns success, yeah? So the first one returns failure, the second one returns success, so this one is success. Great. Then we are going to move to the next one. Yeah, the next one is another fallback, so we are going to analyze, is the ball grasped? Then this ball grasped, we can check down here, it's going to return failure as well. Yeah? So this one is going to return failure. We are going to move to the next one, which is grasp ball. And this grasp ball, that we have it, yeah, so grasp ball, it's here, it's going to return success. All right? So at the end, this one is going to also be success, so this is going to be success, yeah, because both childs are going to be success, okay? Then this one is also success, so we are going to move to the last one, which is place ball, and place ball is also going to return, as you can see here, is going to also return success. So at the end, we are going to end up with everything, with all the childs at success, so the behavior is going to success. And we can also see this here. Yeah? So the first one returns success, this one returns failure, so we approach to the ball, which is success, grasp it is failure, so we are going to grasp the ball, which is a success, and then finally we have the place ball, which is a success. Yeah? Do you see the general idea of this behavior? Yes? Yes, this is very cool. Yeah, I agree, Garrett. This is very cool. And it's going to get even more interesting in a moment. So stay here. All right. Now, let's skip. Well, yeah. This is just a graph that shows the abstraction stack of behavior trees. But let's move down here so that we can analyze a little bit more this sequence and fallbacks that we have just tested. Yeah. So the sequence nodes act as an AND operator. Yeah. So if we have three childs, child 1, child 2, and child 3, we need the three of them to succeed in order for the behavior to succeed. Yeah. If for instance, if the first one fails, then the behavior is going to fail. Okay. And child 2 and child 3 are not going to be executed. If the first one succeeds, but the second one fails, then the behavior is going to fail, and child 3 is not going to be executed. Yeah? You can see this in this graph down here much more clearly. Yeah? So, if the three childs succeed, the behavior is going to succeed. If one of the childs fails, the behavior is going to fail. Okay? See? And this kind of behavior can be modeled into the XML logical implementation like this, with a sequence tag. Yeah? As we have just seen in this first example. Yeah? We have here the sequence. All right? Then, yeah, so we have here another example that we can run, which is BT-U2X2. Let's run this other behavior. In this case, I only have the task 1 executed. Yeah? So this behavior is modeling this. Okay? Then let's have a look at the code very quickly, at the code implementation. Here, in this case, it's the BT-U2X2 CPP. Okay? So let's open this second script, and here we have the implementation again with the include of the behavior tree headers, and we have the different classes. We have the class robot task 1, class robot task 2, and class robot task 3. Yeah? Then in this case, robot task 1 is going to return failure, and robot task 2 and robot task 3 are going to return success. Yeah? So task 1 is going to return failure, and task 2 and task 3 is going to return success. Yeah? And here we have the basic implementation. So we have our behavior, which contains a sequence of the three robot tasks. Robot task 1, robot task 2, and robot task 3. So what is going to happen if we execute this behavior? Oops. What is going to happen? So what is going to happen is exactly the output that you are seeing here. Yeah? Why? Because the behavior is going to start from the first task, of course, and the first one is going to fail. Yeah? So task 2 and task 3 are not going to be executed, and the behavior is going to fail. Exactly. Yeah? Now, let's see yet another example here of the fallback, yeah, which we have seen also in the first example, this fallback. So in fallback, we can have again 3 tasks. Task 1, task 2, and task 3 as childs, yeah? But these fallbacks work like a logical OR operator, okay? So, if the first task succeeds, the behavior is going to succeed already. Okay? So, task 2 and task 3 are not going to be executed either. Yeah? This is task 2, by the way. This is a typo here. It's task 1, task 2, and task 3. Yeah? So, if the first task returns success, the behavior is going to already be succeed, so the other tasks are not going to be executed. Yeah? And for instance, another behavior would be that the first task fails, yeah, but the second one succeeds, then the behavior is going to also succeed. Yeah? Okay, so how do you define these kind of fallbacks in the XML logical implementation? Like this, with the fallback. Okay? Then here we have another example, which is exercise 3. We can open exercise 3 here as well in the code editor. And we are going to see the same with robot task 1 returning failure, robot task 2 returning success, and robot task 3 returning success. And in this case, instead of a sequence, we have a fallback. Yeah? So what is going to happen in this case if we execute? Does somebody know? What is going to happen in this behavior? It's going to be a success, this behavior. How many tasks are going to be executed? 1, 2. And I'm going to say success because of task 2 success. That is correct. Yeah. So this behavior is going to be success because the second one is going to return success. There should be 2 that pass, but 1 fails. Kind of, yeah. So actually, only 2 tasks are going to be executed. Yeah? Only task 1 and task 2 are going to be executed. Yeah? Task 3 is not going to be executed. It will stop at task 2. Exactly, Amna, exactly. Exactly. Yeah, so let's come here and run it. BT X3. So we are going to see task 1, only 2 tasks are executed. Yeah? Because task 2 returns a success already. Yeah? All right, very well. Very well. I see that you are getting the idea because of your answers, which is great. Okay. Then we have more or less 10 minutes until the end of the class. So let's finish here with an exercise where we are going to combine behavior trees with ROS2, okay? So here comes the meat and bones of the class. Then, in this case, we are going to implement a behavior like this one. Yeah, we have the root, and here we have a reactive sequence, okay? What is this? This one we have not explained it, okay? But I wanted to include here this one, so that you can have a taste of another one. But basically, the reactive sequence is very similar to the one that we have explained here, which is the sequence. Yeah, it's very similar. It's very similar in the sense that it also acts like a logical AND operator. Yeah. So basically, this reactive sequence, it's like an improved version of the sequence, let's say. Okay. This reactive sequence that we have here, it also needs all the childs to succeed in order to succeed. Yeah? The difference is that the reactive sequence is asynchronous. Yeah? So it's going to be constantly checking a specific condition in order to succeed. Yeah? So let's see the scenario. Well, first of all, let's have a look at the code, okay? So here we are going to run this test unit 1, okay? So in order to have a look at this code, we are going to come again to the code editor. Yeah, let me close some of these to have this cleaner. And now, instead of behavior tree CPP, we are going to open the behavior tree underscore ROS2 here. Okay, behavior tree underscore ROS2. And inside here, we are going to open the test folder. Yeah? And inside here, you're going to see that you have this test unit 1 CPP. Okay? So let's open this one. All right. Then, here, if we have a look at this graph for this behavior, we see, first of all, we have here this set blackboard, okay? This is used in behavior trees basically to define a specific variable, okay? In this case, we are defining a variable interface, which value is 360, okay? This is like defining a variable that can be used by the rest of nodes, okay? So nothing too important here. This is just defining this variable. For instance, this variable, we are using it here in this rotating node. Yeah? See, this rotating node has one input interface, which is the one that we are defining here. Okay? Then, besides this blackboard, we have here a reactive sequence. Well, we have one reactive sequence, first of all here, which ends up moving the robot. Yeah? But in order to reach this move robot node, the previous ones have to succeed, right? Because this works like a logical AND operator, as we said. Yeah? So in order to have the robot moving, the previous nodes have to succeed, right? Otherwise, we are never going to reach this move robot node. And here, we have this other reactive sequence. Yeah? Then this reactive sequence is only going to succeed when both childs, rotating and reading laser, succeed. Right? Yeah? So basically here we have three main nodes. Yeah? We have this rotating, reading laser, and move robot. Right? Do you agree? Yeah? So far so good with the analysis? Yes. Okay. So now, if I go to the code, which is this one, test unit 1 CPP, First of all, I'm going to find many includes of, so here I have many includes of course, of the behavior trees. Yeah, we have this one, for instance, which implements behavior trees for ROS2. We have many other includes that are related directly to ROS, including ROS messages and so on, okay? But if we come down here, we are going to see the classes as well, yeah? So, as here, as in the examples without ROS, for each node, yeah, for each node, we need to have its class, right? So, we have one class here, which is reading laser. Yeah, it's this one, reading laser, right? Oops, sorry. Okay. The difference is that in this class, we have callbacks. We are defining a ROS subscriber, for instance. Yeah. So inside this reading laser class, we have a subscriber to the scan topic. Yeah? And then we are storing these laser values into some variables. Yeah? So in these classes, we are doing ROS stuff, actually. Okay? Yeah? Because here in these examples, the classes are just very simple. So in this class, all that we are doing is to print something into the screen. Yeah? So here we are doing actually ROS things. In this case, for the reading laser class, what we are doing is to subscribe to the laser, to the scan topic, to the laser information, and then we are storing this laser data into some variables, okay? And then we are analyzing this data to decide if the node is going to return success or failure. Yeah? We are doing this down here, see? So this is the return of the class. Then, if data1 is bigger than 2 and robot angle is bigger than 180, yeah? So if these two conditions are met, my node is going to return success. Otherwise, it's going to return failure. Okay? Just to simplify things, this is the robot angle, which is 180 degrees, and this is the reading of the laser right in front of the robot. Yeah? So if we go to the simulation here, the front of the robot right now is this. This is the direction in front of the robot. Here. Okay? This red arrow indicates the front of the robot. Yeah? So, the laser reading in front of the robot has to be higher than 2 meters. Yeah? This is what this condition means. The laser reading in front of the robot has to be higher than 2 meters. And the robot angle has to be higher than 180 for this node to return success. Okay? Yeah? Then we can analyze other classes. Here we have, for instance, the move robot node. Yeah? This is another node that we have here, and we have it also defined here, move robot. Yeah, in this case, this move robot is subscribed to odometry, and it also contains a publisher for the command bell topic in order to move the robot. Yeah, so basically here you can see the velocity. Here we are applying a linear velocity in the x-axis. Yeah, so this node, what it's going to do is to move the robot forward. Yeah, and down here we have the rotating class as well. Rotating class. Yeah, and this class, what it's going to do, it's also subscribed to the odometry topic, and it also has a publisher right here to the command bell topic. And in this case, I am applying an angular velocity. Yeah, angular velocity in the z-axis. What it's going to do is to make the robot spin. on its z-axis, right? Okay. Then once I have defined all the classes, I have my XML implementation. Yeah? So in this case, we have the behavior tree, we have a reactive sequence, yeah, which is this initial reactive sequence, right? Then inside this reactive sequence, we have a blackboard. Here we have it. And another reactive sequence, right, which is this one here. And this reactive sequence contains two nodes, which are rotating and reading laser, right? Rotating and reading laser. And then finally, after this second reactive sequence, we have the move robot down here. Yeah? And then finally, we have the main where we are registering all the nodes and so on. Okay? Yeah, more or less. Do you get the general idea of this code and how this is connected to this behavior? Yes, more or less. Yes, says Amna. I'm seeing how this could be useful with robotic decision making. Yeah, for sure. For sure, Garrett. This is directly related to robotic decision making. For sure. Yeah, so in this case, yeah, so Anton is asking about Groot, which is this tool that you can see, which allows us to monitor these behaviors, okay? So in this case, it's going to be too much because we are already on time, but let me just tell you that in the course, all this is explained, okay? So in the course, actually, we are using Groot, okay, from the beginning, and all this is explained, how to use Groot and how to load it. This is one of the units. See, this tool here is Groot, which is a very, very convenient tool for behavior trees, as Anton is suggesting, and it's vital for visualizing, for monitoring, and so on. And see, yeah, but unfortunately there are too many things. So I just want to have the chance to finish this example, so that we can see it working in with this behavior tree integrated into ROS2. Okay, so the expected behavior, what is going to be? So what I expect is that the root is going to send a tick down here to the reactive sequence, first to the blackboard, then it's going to enter in this reactive sequence. And then the first one is that the robot is going to start rotating, right? And then at the same time, it's going to be checking this reading laser. Yes? So at the same time that the robot is rotating, it's going to be checking this reading laser. Yeah? And this reading laser class is only going, if you remember, this is only going to return success. Where do I have it? This is only going to return where it is. No, it's reading laser, sorry. Reading the first one here. Yeah. So this is only going to return success if data 1 is higher than 2 and robot angle is higher than 180 degrees. What does this mean? This means that the distance in front of the robot has to be higher than 2 meters, which is not the case right now, right? Because this wall is closer than 1 meter. And the robot angle has to be higher than 180 degrees. So this position right now is 0 degrees. So the opposite one is going to be 180 degrees. So basically, the robot has to be facing this area here, right? It has to be facing this area here. It has to be looking in this direction, and the distance of the laser has to be higher than 2 meters. So right now, with the current scenario, do you think this is possible? It's not. It's not possible. Right? Because the robot is surrounded by these walls. So to start, this first condition is never going to be met. Right? Then what happens? What happens is this never returns success. That this state is never going to be success, so we are never going to reach this last node, move robot, right? Yeah? Does it make sense? Correct. Okay. Now, let's execute the behavior. Let's actually execute the behavior. So let me come here. Let's come here and execute the behavior. Test unit 1. Okay. There we go. Okay, let's have a look at the simulation. So as you can see, the robot is starting to rotate on its z-axis, right? Then how can we make this state be success so that both of them are success and we can move on to the last state, which is move robot? Amna says we need to remove the backward wall to start moving. This or rotate the robot until it finds a space higher than 2 meters in front of it. Yeah, but this is actually not possible if we don't remove a wall, like Amna is saying, right? So if we don't remove any of these walls, this is not going to be never true. Because these walls are closer than 2 meters to the robot. Now, which one we have to remove? We have to remove this one. Why? Because this one is the one where the robot angle is higher than 180 degrees, which is the other condition. Yeah? You see? So, let me actually come here and manually delete this wall. So what is going to happen now that I have removed this wall? Voila! This happens. So what just happened, by removing this wall here, I am allowing the laser to get a reading which is higher than 2 meters, which is in this direction. Then when this happens, this state returns true, so both childs are true, then this one is true. And then we move to the last one, which is move robot. Yeah? And let me now stop it. Yeah? Yeah, do you understand what just happened? Optimal waypoint planning. Yes, very interesting. Yes, I see it was able to detect the open space and move. Exactly. Yeah, so you can see, this is just an example, but here, with this example, you can see all the power that behavior trees have. Yeah, so you can define a robot behavior based on many different things, and so you can basically define complex behaviors with a very high level of abstraction. Yeah. So yeah, I think I'm going to leave it already here. We are past the time of the class, so I'm going to leave it here. Then, so you can keep, as I already said at the beginning of the class, you can have a look here at the project. You can keep working on it. You are going to have this project forever, so you can access it whenever you want to review it. And yeah, and if you are interested and you would like to learn much more in detail about all this, I also left here at the end of the project, I left here a link to the complete course of behavior trees in ROS2. Super interesting course where you are going to learn many more things that are involved into behavior trees. Very interesting course, brand new. We have just published it this week. So yeah, if you're interested, check it out. All right, and yeah, so. Yeah, super cool. Need to spend another hour. Yeah, so it's a super interesting concept, these behavior trees, but it's also pretty complex. Yeah, so it has many layers, many things. But yeah, at least I hope that you've got a general idea with this class, which was my intention. And I also hope that you have learned something and that you have enjoyed this class. And yeah, so thanks a lot, as always, for attending. And I will see you next Tuesday with another open class. As always, until then, take care and keep pushing your ROS learning. Bye-bye.